Hello, my name is Alberto Torrado of Javier Rivera's Evening Physics class, Section 3. My podcast will be pertaining to the conservation of momentum dealing with collisions. Let's start off by explaining what momentum is. Momentum simply is inertia in motion. Now, inertia is a quality that every bit of mass possesses. It is the resistance to any change in motion. Momentum can also be explained as a mathematical equation. P, momentum, equals mass times velocity. If a truck has a consistent acceleration, because of its mass, something small like a car will do little to stop it. This is because the truck's mass is so much more than that of the car. But now take that truck and include more cars, and the truck can now be slowed down to a stop, as seen here. It is clear that the truck loses momentum because the damage to the cars is not consistent. The first two cars get completely obliterated, while the last three keep most of their integrity. The conservation of momentum states as follows. In the absence of an external force, the momentum of a system remains unchanged. So provided that there are no external forces or any unpredictable variables, the total momentum before collision will in fact always equal the total momentum after collision. Within this system, with no external forces acting upon them, there exist two types of collisions, elastic and inelastic. Elastic collisions are simply collisions in which the objects colliding do not stay together, but rather bounce off each other, kind of like hockey pucks colliding or two pieces of ice on a marble countertop. Now, inelastic collisions are pretty much the opposite of elastic collisions. Instead of the objects bouncing off each other, some momentum is changed to heat, sound, or mostly sent right to the other object. This type of collision is typical with vehicles due to their design, which allows the vehicle to deform in order to reduce impact to the drivers. Now we can look at a few examples here. Figure 1 shows a red car losing half its speed after hitting and sticking to the blue car, which is standing still. They deform and slow down, which makes this an inelastic collision. In Figure 2, the blue car is now moving at half the speed as the red car is in the same direction. As a result, the momentum after is the median between the red car's initial velocity and the blue car's initial velocity. And in Figure 3, both cars are speeding towards each other, but the blue car is half the speed of the red car. As a result, the cars move in the direction that the red car was traveling at half the speed of the blue car's initial velocity. Looks like it's experiment time. We're going to go now to the super high-tech 3D pool billiard room where I can show you these collisions firsthand. Alright, here we go. Yeah. Alright, well it wasn't that good, but you can see all the collisions that are happening over there. Because of the friction on the table, they're all slowing down. Let me turn the paths on so you can see it. That way, yeah, there we go. That way you can see how the white ball changes direction after contacting with the yellow ball. The yellow ball is going to continue going straight because of because of the angle of the shot, I was able to go straight. I'm going to get this blue ball here. That's just going to go right in. Boom. See how it bounced? The white ball bounced off the wall and hit the red one. Alright, there's a long shot here. You see how the white ball goes immediately to the left? It's because it's transferring all its motion that I'm hitting with the stick right through to the other ball. The other ball is receiving. It's like I'm hitting the other one without even touching it. And this one here, boom. That's what I'm talking about. Well, that's pretty much it. We covered the difference between inelastic and elastic collisions. We learned that momentum never changes from the beginning of collision until after the collision. And we also had an awesome round of pool, which also provided tons of examples of collisions. So, popcorn player!